Example M7.3, a smooth 2 kilogram collar shown fits loosely on the vertical shaft. If the spring is unstretched when the collar is in position A, determine the speed at which the collar is moving when y equals 1. If A is released, it is released rather from rest at A, okay? And B, if it is released at A with an upward velocity of 2 meters per second. So part A means that it's just released from rest, and then part B means you're pushing it up before it goes down. All right. So luckily for us, we can identify that the only forces acting on the collar are the weight and the spring force, right? So since there is no friction, okay, this is a system that conservative forces are only acting on, right? So therefore, we can use the conservation of energy. Okay, so next, what we have to do is that we have to determine the potential energy. All right, so first we will set the datum to pass through AB. For convenience purposes, you can choose the datum here, or at any point along the in the figure, rather. But I will choose AB. I will choose to use a datum passing through AB, so as to make the calculation of the potential energies easier. Okay, so this will be the datum line. All right, so let's go and analyze this first. What's gonna happen? So if you let this go down, it's gonna stretch, right? And the stretch that will happen, it will stretch by a certain length. Okay, that is longer than 0.75. All right, so when y equals 1, remember that this is y equals 1, this is 0.75, we form a right triangle, right? And therefore, you can solve the deformation, right, of the spring here, okay, let's say SBC, by taking the length of the hypotenuse, which is 0.75 squared plus 1 squared, right? And then subtracting it from the subtracting the original length from this quantity, okay? So 0 minus 0.75. All right, so this should not be difficult for us to understand, okay? And that is 1.25 minus 0.75, and therefore SCB is just 0.5. Okay, so for part A, potential energy, datum is established through AB. When the collar is at C, the gravitational potential energy is, okay, negative mgy. All right, so again, going back to example M7.2, since the gravitational potential energy is very dependent on the y coordinate of the particle, since we set the datum through AB, this length of y equals 1 would be negative because it's below the datum line. Okay, so that's why this is negative mgy, since the color is below datum, and the elastic potential energy is 1/2 k SCB squared. Okay, so here SCB or SBC or whatever you want to call it, for as long as you know it's the deformation in the spring, represents the stretch in the spring as shown in the figure. Okay, so next we can then apply the conservation of energy to the 2 points, right? So point A and point C. So we have TA plus VA is equal to TC plus VC. So at A, it starts from rest. Remember, this is part A first. At A, it starts from rest. Therefore, there is no kinetic energy. Okay, so that explains 0 here. And then it is located at the datum line. Therefore, there is no potential energy due to gravity. Also, it's unstretched. The spring is unstretched at that point. Therefore, there is no potential energy due to the spring force. Okay, but at C, it's going down at a speed vc. Okay, so that is what we want to get. We have 1/2 mv squared, so that's tc, plus the sum of potential energies, or the potential function, which is 1/2 kscb squared minus mgy. Okay, so we know why this is positive and this is negative already. Okay, so plugging in values, you should be able to arrive at a VC of 4.39 meters per second downwards. Okay, now let's say let's move on to part B and say that it is released with an upward velocity of 2 meters per second. That's no problem, because we only need to change this TA in the conservation of energy equation. Okay, so that's 1/2 mva squared, okay, plus 0 plus 1/2 mvc squared plus 1/2 kscb squared minus mgy. And then substituting values, you will find that the vc is 4.82 meters per second downwards. Okay, which is slightly larger than the vc when it's released from rest, because this goes up, and then the elastic potential energy, and then the added gravitational potential energy will contribute to the kinetic energy at point C. Okay, so that's why this is bigger.